The BritChips podcast is proudly sponsored by Silicon Catalyst UK. Hello, I'm Anthony Miller, and welcome to the BritChips podcast, where I have conversations with movers and shakers in the UK semiconductor startup scene. Now, when I was chatting to my next guest in preparation for this podcast, I asked him what useful purpose the technology he's developing actually serves. And he said, well, we can turn wiggly lines into something really useful and really important. And from that point on, I was totally hooked. And I think you will be too. So let me introduce James Lewis, co-founder and CEO of Oxford-based semiconductor startup RED Semiconductor. James, welcome to the BritChips podcast.
Thank you very much. It's a delight to be here and to have the opportunity to talk a bit more about what we're doing at RED Semiconductor.
Look, before we even get into discussion about wiggly lines, why don't we talk about how you ended up leading RED? Because this is not the first startup you've been involved in, is it?
Not at all. No, I've bounced between other people's startup companies and my own startup companies backwards and forwards several times during my career. So once upon a time, I was an engineer. I used to design circuits, mostly analog things, and hold soldering irons at usually the right end and things like that. Then I decided I got more interested in the companies that we were working with, our customers, than I was in the actual hands-on engineering. And that made me seek out a job where I could spend more of my energy in figuring out what customers actually needed. And that took me into the first, was it still a startup? I'm not sure but I joined MEMEC. And that was in the second half of the 80s. And
what did they do?
A distribution company. It was Dick Skipworth's empire, I suppose, of distribution companies, where he'd set up the organization such that each subsidiary of the organization was about a certain size and a certain dynamic of teams with product lines to distribute. And within those companies, everybody had a bottom line responsibility, and you knew it. And the training for future entrepreneurialism was absolutely fantastic, because you knew what your contribution was, and you knew whether you were making it or not, because it kind of corresponded with whether you got paid at the end of the month or whether you kept your job, I suppose. But it was a fantastic learning environment.
So that very much gave you the commercial focus that you've got now, isn't it?
It absolutely did. So I joined as a field applications engineer, which meant that every day I had my nose in other people's projects, learning what the markets were doing. And it meant that as a field applications engineer, I was very much involved in solving customer problems with the resources and product lines that we had at the time, and making sure that I was filling the needs of customers. And that's a lesson to learn that stayed with me ever since. But
you were very aware of the focus on the bottom line. I mean, even though you're a field engineer, that had been kind of instilled in you. The culture of the organization was, don't forget, we have to make a profit.
Indeed. And you worked in a small group, so everybody knew what everybody else had to do to hit those targets and goals. And that really was a great environment. And I suppose to this day, you would look around and you see an awful lot of people who are perhaps sort of my generation, my age, who became startup entrepreneurs, originated from that MEMEC environment. There's a lot of it about if you care to look.
Well, actually, I didn't know that, because a lot of the ones I speak to, actually, many of them certainly of an age, came from ARM, which seemed to be the breeding. But I shall make a note about MEMEC.
Well, yeah, and actually, MEMEC was there before ARM. It was almost circumstantial, because I applied for and was offered the job of an FAE on a programmable logic device line.
FAE as in Field Applications Engineer.
Engineer, yeah. And I turned up on day one, and they said, "Oh, somebody else who works here wanted that role, so you get his leftovers." After after a couple of minutes of pondering that, I said, "Well, all right, bring it on." And that chucked me straight in the deep end with 32-bit microprocessors and application-specific integrated circuits, which have formed the basis of my career to this day. So actually, it was really good that happened. The circumstances behind it are probably lost in history, but it was a very happy coincidence for me. So during that time of learning about the sort of connections between customer projects and microprocessors and ASICs and chips, that formulated some thoughts in my mind. I set up a joint venture with the design team who were designing chips at the Harwell Laboratories, which at the time was the Atomic Energy Authority. Funnily enough, about 200 yards from where I'm sitting right now. And we progressed with providing design services to customers. But in those days, it was really difficult to get customers into the design group here at Harwell. So as all good startups start, we were in a pub one night and we said, should we just do this ourselves? Should we start a company? And we did. So it was myself and my co-founder was the technical lead in the design center. And that's how Oxford Semiconductor was born. So we set the company up in 1991 and eventually exited through a trade sale to a NASDAQ listed business in America. Day one, it was the two of us in a tiny little room with a desk each. And by the time we exited, it was 150 people in worldwide offices. And we were turning over north of $50 million a year.
Wow.
Yeah.
A real result. Well done.
Yeah. It was great fun doing it. And it took me out to California for a few years. I lived on the west coast of America and thoroughly enjoyed that. Spent an awful lot of time in Silicon Valley where you can't help but learn more. Every day is a school day in this business, and everybody you meet is your teacher. So it was a really fantastic experience and thoroughly enjoyed it.
But you've lost the suntan though. So what happened? So what happened next? You exited. You must have been wondering. Yeah.
So after that, I was doing a bit of consulting for 2 or 3 companies and non-exec directoring. And one of those roles was as a non-exec in a company that was called NXT PLC.
The NXT?
Yes. So that was one extreme to another, going from startup world to an established PLC. But I'd never tried a PLC before, so I thought that would be interesting. It was hard work. And having arrived there, it was a company that was in serious need of a turnaround. Frankly, it was on its last knockings in terms of direction and financing. So we figured out what to do with that, did it for a bit, and then we actually did the reverse of an IPO. We took it off the market, privately funded it, changed its name. That became, initially we called it High Wave while it's still a PLC to indicate that things were changing. And then we called it Redux when we delisted it and built that up into a substantial company, eventually sold that to Google. So,
Google? How long ago roughly was that?
That was in August 2017.
Wow. And you still didn't get fed up with the industry because you carried on. Yeah. Sort of in and out bit. So I think the next biggish thing I did after that was again join somebody else's startup, which was Helix. And it was a bit of a departure for me. It wasn't a chip company. It was a
an antenna company. But it was fascinating. It was a really interesting technology in antennas. But we ended up actually with two businesses in one. One was the science and technology of the design of these antennas, and the other half of it became a manufacturing company. How do you make these things? And
And these antennas were used for what, mobile
they
phones
were
or?
LRAD, so it was GPS. So
Okay.
and the objective being to reduce the impact of interference or jamming or reflections, the things that cause problems when you're trying to navigate your way around a bunch of streets at the bottom of tower blocks in London or New York.
When you say
So,
jamming, you're kind of implying they're malicious jamming?
yeah, and uh, yeah, looking into the malicious jamming challenge and how you're going to deal with that, and actually, we think about GPS as where we are, but the terminology of position, navigation, and timing, the third of those words, is extremely important and often overlooked. So network timing for City of London transactions in trading floors, um, all of that and blockchain will be coordinated against timing, which is probably taken off satellites. It's either comes via fiber optic from Greenwich, if you're lucky enough to have a fiber optic into your site, or you're getting it off the atomic clocks on the GPS satellites. So if you can jam somewhere, in the middle of London, you can basically bring. I'm not sure I should be saying this, but it's kind of. But you could bring to its knees until somebody figures out who's jamming it and what to do about it. And that there are many people, organizations concerned with this and trying to fix it. So what that led to was a concept in that company whereby we could, with an array of antennas, small array of antennas, we could detect the angle of arrival of an incoming signal, and then we could work out whether it was a genuine or a bad signal.
From the
Noise.
direction it came in?
Exactly. So jamming is just jamming. It's just a noisy signal. But the clever one would be a spoofing signal where the data stream looks like it's a satellite ephemeral data stream, but it's not. It's false. It's been reorganized to give false positional information. And what a satellite's telling you is what the time is, and its orbit equations. So you can say, well, the orbit equations, that satellite means 1 second is here, another second is there, another second is there. And if it's doing that, if the angle of arrival of the signal corresponds to that, it's a good satellite, it's actually the one that you're navigating on. If it's not, it's a spoof. And that's a really difficult thing to do. Yeah, it's difficult maths. And you've got to correlate the signal into your array of antennas. So that got me thinking about how you could process that on a chip. So I guess I was somewhere thinking, could we turn this company into a chip company? Because
That's what you
I
do.
used to antenna companies. And for that, we'd have needed probably multiple processor cores to process the inbound signals and to correlate them accurately and to do the phase difference mathematics to work out what we needed to work out. So that got me looking at microprocessor architectures again, and the obvious one was ARM. But as a little tiny impoverished startup, we were never going to afford an ARM license. So I revisited people I knew in the industry, came back across a former colleague, David Calderwood, who was working with an open source project to consider microprocessor architecture instruction sets. And we thought, could this be of use? It was an open source project. Could this be of use? Could we could we turn this into something? And we we wound that whole thought process on quite a lot and decided that there was something in there that we could commercialize, and thus RED Semiconductor was born.
So it
And
sounds like Helix kind of went on its merry way doing whatever Helix
yeah,
was doing.
it's
Yeah.
making its antennas and all is fine and dandy there. So um, it was an easy decision for me to jump back into the world of semiconductors.
Yeah, well, it sounds like a bit of a light bulb moment. I mean, certainly meeting David, who has had the kind of access to the open source work that was being done, you basically very keen to get back into the chip business and the idea. You saw the problem, and now you wanted to go and solve it. So when was it that I guess you and David formally got together to create Red?
Well, we informally got together in 23, and we sort of played with some concepts and ideas through 23. By the end of 23, we knew what we were going to do, where we were going to go with it. And in January 24, we formed RED Semiconductor International Limited, which is who we are today. And that's the company that we're exploiting the technology through.
Now I'm going to ask you the question that your COO David did not want me to ask you. Why did you call it Red?
Um,
It's such a great story. It's such a great story, James. You got to tell it. Mm.
Well, in much the same way as you might ask the film company, whose name is Working Title, why did you call your film company Working Title? And it's because they had a working title, wrote working title down, and it just became it. So we were chatting away one evening, looking at whether we could or should form a company, and somebody said, "Well, what should we call it?" And I suppose by that point, the other people involved, because they got involved were able to be involved in the open source project, just because they didn't have to go to work every day. They were retired. So David said, "Well, we're retired and extremely dangerous, like the movie." And so our working title became RED Semiconductor, and it just stuck.
You have to be a Bruce Willis fan, but it's wonderful. It's one of the best rationales for a name I know of. So anyway, how many of there were you actually at that startup time then?
At that time, there were 4 of us.
Okay,
And
and was that the dream to produce a microprocessor basically that could be used in that sort of antenna application for detecting spoof signals, or was it broader
well,
than that?
it was very much broader than that. At the time, I think there was a recognition that that there were certain limitations in processor architectures, and things were changing in the dominance of established architectures was potentially going to be challenged by open source architectures. And we then spent time sort of reviewing architectures and the direction of architectures, and we recognized that really the best route to follow, though it wasn't necessarily the first route we followed, the best route to follow was definitely the RISC-V architecture, because even by that time it was so well established and so many people were being trained and developing skills around the RISC-V architecture.
Now, I'm
So
not a semis guy, but funnily enough, I knew the term RISC because back 50 years ago when I was working for IBM, RISC was known there. They developed some of their mini computers on RISC, but RISC-V sounds like to me version 5. Has that become some sort of de facto architecture now for microprocessor design?
I don't know where the 5 comes from. Interestingly, you mentioned IBM, because the IBM architecture was made open source. It became the open power architecture, and that was the one that
That's right.
the
That's right.
the original open source project was looking at. But the feedback from the market was very much that that was the wrong architecture to look at. RISC-V came about actually as an educational training environment, and was developed, I believe, at the Berkeley University as a way of taking students through the first principles of both hardware and software architectures. So the physical hardware architecture and the instruction sets and how they interact in that. And it was a very simple, straightforward architecture and not many instructions. So obviously fitted the RISC bill. I don't know why they called it 5, and I don't know where 1, 2, 3, and 4
Ever went? Yeah.
so but it has become established as a core processing element for so many things. You know, there are companies embedding RISC-V in many applications. There are exciting companies hyperscaling it, you know, putting hundreds, if not thousands, of cores onto a chip and making things that I suppose challenge the potential of GPUs in large-scale data processing. So it has a huge promise.
So what
And
are you doing? What is RED doing with it then?
so we are simply using it as an embedded controller within a unique architecture that we've developed for mathematical acceleration. And the reason for this, and now this sort of comes back to the vision of the market and the opportunities for us. But if you think about there are two driving forces. One is the predominance, I suppose, of AI in almost everything these days, and the fact that the specter of AI consuming huge amounts of energy in data centers in the middle of deserts with power stations built right next to them to power this, and the concept that such huge amounts of power are going to be needed for AI. But we've got to figure out what AI is. What AI actually is, and what it's useful for. And I think there is a widespread perception, not necessarily within the industry taking advantage of it, but within the the billions of onlookers on planet Earth, that AI is generative AI. It's ChatGPT type of
ChatGPT,
AI.
yeah.
So whereby human beings like us sit there at keyboards and ask AI silly questions, and therefore AI training needs to contextualize the entire universe so that it stands a chance of answering the question you've asked in the way that you want, and the language that you want, and the style that you've requested.
But you don't want to get into all of that, do you?
We
You have
can.
to, yeah.
So the other end of AI. So one of the things that I think is it's the next wave really of AI, is moving AI to the edge, to the physical edge, where it is invisible and useful. So instead of us all sitting around a keyboard and looking at AI generated pictures and AI generated words and things, AI is just happening there in the background. People call it ambient AI.
I haven't heard that term before, but it sounds like a new form of dance music, but there you go.
Yeah, it does. Yeah. So, but where AI is keeping us safe, keeping us warm, keeping us fed, you know,
So
looking after
what
our
sort of what was
about
going
it.
on in your mind? You say, okay, we're gonna make this. RED is going to make these wonderful microprocessor chips for edge AI, and they're going to be used for this. What was
Well,
this?
yes. What is this? Well, I'll talk about a specific use case in a minute, but general use cases. And in a way, there's a slight connection with when IoT suddenly got announced 20 years ago or whatever.
Internet of Things, yeah.
Yeah. So IoT kind of didn't turn out to be the way it was sold on day one. And I think now we're getting closer to that, but we're getting closer to intelligent IoT. So what happens at the edge, and we'll consider what the edge is in a moment. But in an edge application, you are inevitably sensing. So you've got some number of sensors that are you're then processing the data from those sensors. You're fusing it together to create a situational awareness. So you know that the world that surrounds you, and it's easy to think of this in a visual style. They've got camera sensors pointing in all directions, and your autonomous vehicle perhaps knows where it is. It knows who's running into the road in front of it. It knows where the next turning is, etc. But this can be anything. It can be sensing any physical thing.
It could be temperature, it could be pressure, it could be whatever.
Yeah, absolutely. Uh, And then once you've created your situational awareness, you are looking for changes in it, anomalies. You're looking for patterns or things that are entering your field of vision. So you are now detecting changes going on within within your built up world. And then you need to know what to do as a result of those changes. So again, the autonomous vehicle is the easy one. There's an orange thing moving across the field of vision. If it's a Sainsbury's carrier bag blowing in the breeze, don't worry about it. If it's a football, it's quite likely to be followed by a small child. So do something about it. So you make sense of what those changes actually mean and what decisions have to be made as a result of them. That's where the AI comes in, and you're referencing to training models at that point, and then you're taking an action based on that, and that's all happening at this right at the edge. And then you're almost certainly communicating what you've done and why you've done it into the ecosystem. But that's very valuable data. So you'd better look after it. You better encrypt it. So cryptography comes in. So we've got the data fusion at the front, and data processing. That's mathematically intensive. We've got the AI, neural networks, figuring out what to do,
What it means. Yeah.
Mathematically intensive. Lots of big matrix multipliers going on in there. We've got the action, which is a little bit of maths in that. And then we've got cryptography. We've got the communications of encrypted data. And that is mathematically intensive. So at the edge, you've got this sequence of things, all of which require a lot of maths. And that maths is not suited to a CPU or GPU or TPU or whatever architecture you can think of. None of them will treat this end-to-end data and control of the data.
All those four elements. There's nothing that does all those four elements that you described.
Exactly.
Yeah.
So we wanted to make something that does do that, all of that stuff. So that's really what our architecture is all about. It's the mathematical intensity with the ability to contextualize and control what's going on in that small world.
And it does the interpretation. I mean, it really is the end-to-end thing from the sensing, the interpreting, the taking the action, the communicating, and the encryption. This is what you wanted to design in your microprocessor or microprocessors or chip.
Yeah, that's exactly it. And that's the architecture that we've pumped for. So it's a mathematically oriented architecture. It's an array of highly configurable mathematical elements with a highly configurable fabric that interconnects them. So, and this is where the processor, the RISC-V processor, comes in.
So it's very much for, I guess you'd call it like sense and respond applications, but AI enabled. That's what RED Semiconductor's product is designed for. At the edge to do it. Yeah.
Sense, decide, and respond. So it's not a linear thing. Oh, if this is happening, definitely do that. It's these things are changing. What do we know about it? What do we do about it? So you've got that AI decision process, and then the response as a result of that.
So where are you then in the achievement of this objective? Have you built this thing yet?
We've built subsets of it and tested little bits of it, and we've the the process through a processor architecture inevitably starts off with a software simulation. So you build a simulator um, that performs the job that you're trying to do, which is complex. Sort of a sequence of operations. Uh, the efficiency of the mathematical processing depends largely on two things. One is the sequencing of the operations in complex mathematical algorithms, um, and sequencing it in such a way that you reduce the need to load and store data in memory during that processing. So obviously at the start of it all, we have to load up the source data, and at the end of it, we have to store the result data. But if we can minimize or eliminate the load stores in between that, then you save an awful lot of time and an awful lot of power. Every time you load store, it can, it's latency and power consumption. And a typical processor environment, 50% of the power consumption of a processor or more will simply be your accessing memory cycles.
Okay,
And
so
those
load store as in load data from memory into the processor, process it, and then store it back in memory. That's yeah,
and store it back. So
yeah.
there are a lot of even basic mathematical routines where you're doing the same thing over and over again. So
I'm
you
curious. Can I just sorry? Can I just ask about simulation? This is something just occurred to me. When you said you obviously have to build a software simulation first, is that something you had to build from the ground up, or are there like off the shelf simulator sort of frameworks, and then you can sort of tailor them to your specific need?
there are tools which will allow you to build quite a comprehensive simulator, but usually you have to pay money for those tools. And when you're an impoverished startup, Um, but actually, because of the way we built the concept, so we started with little building blocks, which we were able to then just write a simple simulator for, and then gradually, as the thing built, we were able to join it together. So it was actually a really helpful way to do it, was to write our own simulator from scratch.
Out of curiosity, how long does that take? I understand it. I'm sure it's still under continuous development, but in order to get to the stage where you could run a simulation and say, okay, this works, or we need to tweak that.
I think the first basic simulations of the top level architecture um, were a matter of a few weeks, not a great deal of time. So it's really difficult to put a timescale on it, because it is just a continuous process of building features, and as we solidify features, we 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 we, we take a large block that we originally would have had in the simulator and says, this does this function, and we estimate that this is going to take this many clock cycles to do it. And then you get down into the granularity of it, and you say, to do that function, we need to do this first, then this, then this, then this. And then we add up the clock cycles that those actually take, because we're designing them, and we've got a better reference point in the simulator from then on in. So
Wow.
it's a continuing it's a continuing
Yeah.
development, which is something you wouldn't get if you tried to do this with an off the shelf
No, I
sim.
understand. I understand. Oh, so have you got to the stage where anything is in a hardware form in whatever shape or form?
Yeah, we've done some tests on parts and cut down versions in FPGA at the
Right.
moment.
And that's field programmable gate array, some off the shelf FPGA. Yeah.
Yeah. So so that's proved functionality and efficacy where we've needed to of certain functional elements. So we've known that we're doing that, and that's basically the process of doing that is taking the descriptions that we have developed from the simulations and doing a system Verilog um, implementation of those, and then the gate output of those into an FPGA and making it work.
Now, I've only recently learned Verilog is the sort of the language which actually converts it into something which can program the chip on, isn't it? Yeah. Okay. Again, that's an industry standard sort of thing.
It is, yes. It's a descriptive language with whereby tools are able to take your description and turn it into gates.
Have you been able to trial any elements of this with the outside world, with pilot customers or interested parties or whatever?
We're going through that process right now, and we are again at a simulation level. We're doing exactly that. So a use case which is interesting to talk about because it kind of encapsulates why you need what we're trying to do. We've got a grant funded project running at the moment, collaborating with a biomedical research company. They've developed a technique for detection of various things, from identification and counting of certain types of blood cells. And I don't really understand the sticky end of this, but the output is they're using microfluidics and various sensing techniques, which include electrical impedance sensing and exposure to fixed wavelength light, and then looking at autofluorescence that results from that. So they have two sensing environments with probably multiple sensing frequencies on each. So you try it out with different frequencies of electrical impulses and different wavelengths of light. And then you've got a bunch of data streams coming from the sensors, which you've then got to correlate because they're separated by time and or distance. So you've got to correlate them back into useful information. And the really tricky thing here, this is a needle in a haystack job, because if you...
Well, they're what, looking for sort of abnormalities in the blood, is that it?
Yeah, yes, yeah,
Oh,
yeah,
okay.
yeah. Or certain characteristics in blood cells that reflect where those have either been generated or affected. So very important in cancer therapy.
Oh, right, yeah.
And the difficulty here is that in the therapy that they're starting off looking at, if you take a syringe full of blood and test it, you're actually looking for 10, 20, 30 of a certain type of blood cell in it. And it matters whether there are 10, 20 or 30. So you've got to count accurately. So you can consider that that's well beyond the human boredom threshold, trying to identify 10 blood cells out of 10 billion. And it's nonlinear. And the reason it's nonlinear is because the microfluidic channels have to pass red blood cells, and we're looking for white blood cells, which might be the close side of the channel to the sensor or the other side of the sensor. They might have clustered together. They might have hidden underneath a red blood cell. So you kind of know what you're looking for, but it's somehow superimposed on a lot of noisy background data. Your pattern matching, looking for some specific response, but you can't use filtering to sort of say, well, let's get rid of all the other rubbish, because it's going to effectively be superimposed on it. It reminds me a bit of GPS as a below noise floor. Unless you know what you're looking for, you don't know it's there. So
Right.
you're not going to find it without knowing a lot about it. And that's the training in the AI. It's the parameters of the patterns that you're looking for, and you're going to then detect those in the middle of this noisy data. So,
And
so
that's what you've built the simulation. You got to the simulation. You've got a simulator now that does that.
we have, and actually it made us realize that the version 1 of our architecture wasn't flexible enough, because the requirements, um, as the partner discovered more things about the sense data, we realized that we had to do bigger mathematics on more parameters of both data and training model parameters. So this project's been really important because it's helped us focus on the level of processing of this kind of data that's going to be required.
Do you
Um,
see this project eventually leading to the creation of a real microprocessor chip that serves that function for that partner?
indeed, but it will also serve functions for many other applications. So the chip itself would be universal. The bit that would be specific would be how it was trained. So collaborating with the customer, we'll work out a training model that allows the determination of what we're actually looking for in the data. So you've got a data stream and a set of training model parameters, which basically come out as the weights and biases in your neural network. So the mathematics that's going to take place in that instance is a neural network. And
Wow.
so our firmware in our chip will configure the array of mathematical elephants,
Heavens.
the array of mathematical elements as a neural processor.
Wow. I mean, how long do you think it will be before, the first of these, I guess, prototype chips are rolling off the line in, I guess, faraway Taiwan or wherever?
Well, we we're part of the Silicon Catalyst Accelerator program,
You're
and
part of
through
Chip Start, aren't you? Yeah.
yes, yeah, we were on the first chip start cohort. And
Oh,
then when we
right.
finished that, we applied to join the full Silicon Catalyst 2-year program, which we were accepted onto. So that gives us some great partnerships in the manufacturing side for chips, and also gives us access to, via IMEC and TSMC, access to at least one multi-project wafer run during the time we're on that. So we're actually planning to tape out around the middle of this year.
Oh,
Um,
this year. Fantastic.
yeah, absolutely. So we will have uh, chips back and tested and demonstratable in end of Q3 or early Q4.
Yeah,
So that,
yeah, towards the that's brilliant. And will you be using that sort of application, the blood sensing run or whatever, will be kind of the demo for it, or have you got other ones up your sleeve as well?
we have some other customer driven examples, which I can't go into much detail about, but
No, no.
one is industrial control,
Right.
when, where some high levels of intelligence need to be applied uh, to the, again, situational awareness and the response to that situational awareness. Um, and the other one is cryptography, where we're working with a partner on um, uh, network enrollment, authentication, and encryption of data in a very secure environment.
Because
So
your chip, your architecture includes this sort of cryptography thing for transmitting the data outside of the chip, so to speak, to the big wide world. Did I understand that right?
well, it includes the ability to do that, and then the way it actually gets done is that the firmware says now or the code says now we've got to encrypt the data that we've just made. Um, so reconfigure uh, the mathematical elements into something that does the maths for encryption, and
It
typically
does that within the chip dynamically at the time. It's like
and it,
self configures itself to perform a different process.
yeah, and the configuration depends on firmware.
Right.
So instead of sending instructions down a microprocessor pipeline, which can be done, and you'll send a whole lot of them saying shift this, turn that, add that, multiply this, store it here, fetch it from there, do it all over again. You're streaming a continuous pipeline of data into the processor. In our case, there's one call. It's a library call, because the firmware for this will already have been written and will reside in the processor. And you'll just say, invoke that firmware. That firmware will set the processor up as the cryptographic processor, and then you'll just keep firing data down it, which will get encrypted, and you won't have to write any more instructions. So it dramatically reduces the overhead on designing and writing code, writing mathematical code.
Have you got patents on all of this?
We've got
Or
patents going through.
applications, at least, yeah.
Yeah, yeah.
Because it sounds incredible stuff. Just a couple of other things as we tie up the podcast. Obviously, this costs a lot of dosh. I understand, obviously, being part of ChipStarter now, the Silicon Catalyst program, there's a lot of support and access to facilities that you don't need to pay for, at least not now. But nonetheless, you've got mouse to feed, you've got kit to buy. How have you been funding things up to now?
Well, from the start up until fairly recently, we funded it through the good grace of the founders, i.e., we didn't take anything out of the company, and the extremely small engineering team, 2 of them. We were able to cover from our grant income. So
Fantastic.
it was a small and cash limited rollout of the capability. Late last year, we closed a funding round, which has enabled us to grow the team. So we're now up to 6 engineers in the team, and we're continuing to hire new specific roles. And that's given us the ability to engage with customers, and so the business has taken a dramatic turn for the better.
Yeah. Was this announced at the time how much you raised in that round?
No,
Okay.
can't really announce how much we raised. It wasn't huge, but it was enough. And actually, so fundraising is the thing that every startup has to go through, and it's the worst thing while you're doing it, but the best thing when you get a
When you
result.
get there, yeah. Where
And
will that, with the current funding, where do you think that will take you through? I assume at least until the end of the year when you've got those chips coming off the line, so to speak.
yes, so we have pledged support from our investors to get us all the way to working prototypes on the desk of first customers.
Oh, that's fantastic. And then at that point, I assume it's sort of, once you've proven and hopefully you've got the customer demand, you'll probably still need to get additional funding, because I doubt whether the sales will be able to, generate enough cash at the top, to feed yourselves.
Yeah. Yes.
Did the round you just done, would that count as a seed, or is that a Series A? Where are you?
The round we've just done is actually pre-seed. We're calling it
Pre-seed. Oh, pre-seed. Okay, right.
Yeah. So effectively, it was what got us going from a bunch of guys using their own time to do some R&D and come up with good ideas, to a proper established company that could then afford to take on engineers. So yeah, we'd come a long way on the goodwill of the small team that was involved in it. And
Yeah, and
I
not just the
cannot.
kindness of strangers; it's the kindness of loved ones as well.
Absolutely, indeed, and I can't thank those guys enough, because um, they were vital to getting us through that first period, to the point where we could actually talk with and engage with investors, have the right discussions with the right people, and
Indeed.
move on to the next step. So they did such a vital job of both developing the technology and making the company appear, you know, as a
Fantastic.
whole company that was going to go somewhere. So fantastic, great
I mean,
team.
look ahead now, James. 3 years, 5 years. Where would you like Red to be in that sort of time frame? What's it going to look like then?
We've got some optionality about how we monetize this technology, and
Right.
we have 2 distinct routes. One is IP sales into companies that have got the necessary design teams and resources and applications to use IP in large complex SoCs. So system on chips.
Systems on chips, yeah.
So so that's one of our routes, and we've got some interest from those sort of companies who want, as soon as we can put some evaluation hardware on their desks, they are keen to start working with it. So that would be a licensing model. But alongside that, we're going to make test chips anyway, just to prove the performance in a chip. That's going to be the other end of the scale. It's going to be a simple host processor, again, probably in our case, a RISC-V application CPU with our then RISC-V based accelerator onto a single chip. And that will effectively be a neural network oriented chip. So a very small, very low cost neural processor or neural microprocessor, microcontroller in a way, because it won't just be the neural network standalone. It'll be performing the neural network and doing
The
things, control functions as a result of what's going on with that processing.
You say very low cost. Do you have a price in mind of what you'd like to be able to sell these chips when they're coming off in their millions?
Yes, it would be a similar price to what you would expect to pay for a 32-bit microcontroller from one of the main semiconductor companies. So perhaps the kind of company that uses an ARM Cortex 50 series processor and other microcontroller things around it, and then puts that on the market.
Be very competitive then for the function that it would deliver, which is
quite all the AI function. Yeah.
Well, it's interesting because it sounds like you don't have to make that decision now whether to be an IP company or a chip company, so to speak. And who knows? Obviously, they're quite different business models, and there are pros and cons on both. And be very interesting to see the way that the company develops and your thinking develops along those lines. And I guess it's a decision you refine each step of the way as you get the first customers on board, and then you see there's other applications, and then that will probably in the end say, well, okay, let's go this way, let's go that way.
Yeah, exactly. Yeah. To use the oft-used phrase of the man on TV, follow the money.
Exactly so. Let me ask you one last thing a bit before we sign off, because you've had a lot of experience, not just with RED, but obviously in your previous incarnations as well, as one of the sort of the wise grey-haired men of the semiconductor industry. What message or messages would you pass on to the young entrepreneurs, the men and women, particularly at university now, starting up their own semiconductor startups, like many of the ones you must have met at ChipStart in the first cohort? What would be the most important lesson or lessons you've learned that you would say, if I knew then what I knew now, it would have really changed? What do you think?
It's funny you say it. So it's just reminded me of something. A long time ago, I was talking to somebody at a conference, and he asked me, "What was it? What was the important factor that got you to start this back in Oxford Semiconductor days? What was an important factor in starting a company?" And slightly deliberately, I answered naivety.
If I would have known, I wouldn't have done it.
And then this person stood up with his pitch on the afternoon of the conference, which is a conference to startups, saying what you need to do to be a good startup. And on his list of things that you needed to be, one of them was naive. And I kind of said it as a joke, but actually, if you think too hard about it, you're probably not going to start up a startup.
No.
So it's a bit of a truism, but actually, going on from that and being more sensible about it, you've got to analyze and understand your own capacity for risk and how you can respond to risk. Yeah, don't don't put your house on the line if
Yeah.
you've got a wife and a bunch of kids who kind of need a roof over their heads if it all goes wrong. So understand all the risks involved. It's obviously a risky thing starting a company at all. And then the scale of risk involved in what you're trying to do. The more outrageous your startup idea is, quite likely that correlates with the riskiness of
There is
it
a risk.
and the
Yeah.
risk that there might not be a market ready for it when you've developed it. You're too early or you're too late. So you've got to go through a serious risk analysis. And I think I've come across people who've started a startup because they wanted to start up a startup. That's been, and I'm think, what can I do? I want to start a company. And then they search around and then somehow come up with an idea that they can start a company on. I would turn that around and I would say the thing that I've learned is, if you're working in a technology area and you understand the technology and you understand its route to market and how the market dynamics are going to accept what you're doing, and you recognize that unless the thing that you've figured out gets done pretty quickly, it won't happen. That's the ingredients that you need to then say, there's only one way this is going to happen. Nobody else is going to do it. I'd better do it. That's your trigger for starting a company and becoming an entrepreneur. And all of those things are the points that you'll have to present very clearly to investors to be able to ever get money around it.
Absolutely. So it sounds like it sounds like follow the dream, but understand the risks. I mean, frankly, you'll never understand all. You'll never be able to preempt, or even understand, let alone preempt all the risks. You just have to take a measured view.
Yeah.
But if the dream, the ambition is strong enough, then go for it. And just go for it.
Yeah. And if your dream is simply running a company, go pick an easy one to do.
Yes. And I think on that point, very wise words indeed. Look, James, it's been a really interesting, really wonderful conversation. I think there's much that our audience at all scales of maturity and experience will pick up from it. So James Lewis, co-founder and CEO of RED Semiconductor, thank you very much indeed for joining me on the BritChips podcast.
And thank you.